Hey, hey. Okay, let's go ahead and get started. So today we have like a couple of different mini topics. So we're going to start off talking about degree sequences. So what this is just the list of vertex degrees of a graph. So we'll have a definition, which says that the degree sequence of a graph is the list of vertex degrees written in non-increasing order, so smallest to largest. So as an example, I'm going to ask you to give me the possible degree sequences for graphs up to, simple graphs up to 5 vertices.
You said non-increasing is smallest to largest.
Or largest to smallest. Yeah. So what are possible degree sequences for simple graphs um, up to 5 vertices? So I'll give you a few, hey. You're terrifying. Stop it. I'll give you a few minutes to think about this, and then we'll talk about what degree sequences you found. Hey. Do this. Okay, so what did you find? What's the possibilities for n equals 1 vertex?
Zero.
Yeah, just 0. And then what about n equals 2? Yeah.
Would be 0, 0 or 1, 1.
Yeah. Yeah, and those are the only two choices, right? So I guess like one thing that you can already see from n equals 2 is that not every possibility exists, right? Like you can't have 1, 0 as the degree sequence of a graph. Okay, good. And then what about n equals 3? Yeah.
1, 1, 0, 2, 1, 1, and then 0, 0, 0, 2, 2, 2.
Yeah. Okay, good. Did everyone get agreement with this? And then what about n equals 4? What are the possibilities? Yeah.
0, 0, 0, 0. 1, 0, 0. 1, 2,
Yeah. 3, what did you say? 3, 3? Yeah. Nice. Okay, and then maybe we won't go through the full n equals 5, but I'll ask a question, which is that, is it possible? Actually, I don't even know if this happens in the n equals 5 case, but does the degree sequence specify the graph? So is it possible to have two graphs that are different? They're not in the same isomorphism class, but they have the same degree sequence. I can't even think of an example.
You have like one cycle and then like two cycles.
Yeah, yeah. So like we had different yeah, so maybe we should go to the 7 case. So let's look at this example, these two examples, and n is 7. So in the first problem set, you saw that there are two kind of different ways to write a graph with 7 vertices that is such that it is a cycle or a union of cycles, right? And so these two graphs would have, thinking of this as being one graph with two components. These two graphs have the same degree sequence because every vertex has degree 2, but they're not in the same isomorphism class. Yeah, so it is possible to not have the same degree sequence, or sorry, to be non-isomorphic, but have the same degree sequence. So we're going to investigate that question a little bit more closely. There's more in the book about which sequences can be degree sequences. So if you're curious about that, you could read into it. But we're going to look at the question of if two graphs have the same degree sequence, is there a way to relate those two graphs to one another? So I'm going to give you definitions. This is like an operation that you can do to a graph, and we'll find that this operation preserves the degree sequence, and then we'll also prove that this operation is enough to relate two graphs that have the same degree sequence. So here's how the operation works. So we'll have the definition. So this is called a two switch, and a two switch is the replacement of a pair of edges XY and ZW in a simple graph by the edges YZ and WX, given that YZ and WX were not originally in the graph. Okay, so I'll draw a picture so that this makes sense. So if we had vertices X and Y and an edge between them, and vertices Z and W with an edge between them, and then possibly other stuff going on outside of this. So these circles are just meant to represent some other stuff going on in the graph. Then what I can do, as long as the edges YZ and WX are not in here, is I can just replace the edges XY and ZW by those two edges YZ and WX. So erase those. So instead we would have this YZ and WX. Okay, does that make sense what the operation is? So one observation is that a two switch preserves all vertex degrees. So why is that? At each of these vertices, X, Y, Z, or W, we deleted one edge and then added in a new edge. So we kept the vertex degree at X, Y, Z, and W the same. And the rest of the graph was left unchanged. So any other vertices that are in there also have the same degrees as they did originally. Okay, are there questions? So we're gonna prove the following theorem about two switches and degree sequences. And this is due to I don't know how to pronounce this name, but I'm guessing that it's German, so I think it's probably Berge or something like that. So theorem. So this is due to Berge in 1973. And it says that if G and H are two simple graphs with vertex set V, so we're going to assume that they have the same vertex set. Then we're going to have an if and only if statement. So the degree in G of V is equal to the degree in H of V for all V in V, if and only if there is a sequence of two switches that transforms G into H. Okay, so this is saying if G and H have the same degree sequence, then there is a sequence of two switches that transforms G into H, and vice versa. So if there is a sequence of two switches that transforms G into H, then then the degrees are equal everywhere. Does this statement make sense? Okay, so let's go ahead and prove this. So one direction is easy / we already proved it. So, and that's the backwards direction. So if there is a sequence of two switches, then the degrees are the same for all vertices. And this is just by the observation that we already made, that doing a two switch preserves the vertex degree everywhere. Are we comfortable with this? Are there questions? Okay, so let's do the forwards direction, and this is a little bit tricky. And we're gonna do it by induction on the number of vertices. So let's do the forwards direction. So let's suppose G and H are simple graphs on a vertex set V, and the degree is the same for all vertices. So we're gonna do this by induction on the number of vertices. So what should our base case be? Yeah, so let's consider one vertex. So in this case, there is exactly one graph. So that means that G and H would have to be the same graph. And in the case of this proof, it's actually going to make sense for our induction to start with 4 vertices, because if you think about it, in order to do a two switch, we need 4 vertices to be present. So we kind of need to argue all the way up to n equals 3 that this is already true, and then we can start working with two switches at n equals 4. Does that make sense? So if it's one vertex, it's good. We also need to look at 2 vertices and 3 vertices. So we kind of already went through what the possibilities were, but when there's 2 vertices, there's only 2 graphs. You just have these 2 options. And so if G and H have the same degree sequence, then they're also the same graph. So this case is also good. And then for 3 vertices, similarly, you only have one isomorphism class of graph with each degree sequence, right? So we only have this guy and then one edge and then those 2 and then these 3. So those are the only choices. So if G and H have the same degree sequence, then they have to just be isomorphic. So no 2 switching necessary. Are there questions about the base case? Okay, so let's go to the induction. And we'll consider n greater than or equal to 4. So let's let n be greater than or equal to 4. Okay, so this is how we're going to find a sequence of 2 switches. So I'm going to let W be a vertex of maximum degree. And I'm going to call that maximum degree delta. Okay, so this is in both graphs, W has the same degree. So it's not confusing to speak about just like the maximum degree. We mean that for like, it's the maximum degree in both graphs. And then I'm gonna let S, and I'll denote this by V1 up to V sub delta. Okay, so we're taking delta many vertices, and this is going to be the set of vertices with the highest degrees other than W. So be the vertices with next highest degrees. Okay, so I'm going to make the following claim, and then we'll prove the claim. So the claim is that there is a sequence of 2 switches accomplishing the following thing. So it's going to, this sequence of 2 switches is going to transform the graph G into one called G star, such that G star satisfies the following thing. We want that the neighborhood in G star of that vertex W that we picked out, we want this to equal S. And we're going to have the same claim for H. So similarly, and there is a sequence of 2 switches transforming H into H star. Such that the neighborhood in H star of that vertex W is also equal to S. Okay, so let me draw a picture kind of what's going on. So let's say we're looking in G. So here's our vertex W of highest degree. And here's our set S of the vertices of next highest degree. Okay, so it could be that W has edges to some vertices of S, or it could have vertices to some things that lie outside of S. So let's say this is our set S. And then let's say W is connected maybe to some other vertex over here. And then possibly also we have vertices lying over here that are not equal to W, connected to W, or an S. So we might have something like that. Okay, so this is kind of the setup, and we're gonna argue that there is a sequence of two switches so that I can get all of these edges coming out of W to be going to the set S. Do you have a question?
S from just circled like all five of the vertices, like what's S is defining, right? You said it's like
S is supposed to be the,
degrees.
yeah, so it's like the vertices with highest degrees after W, and we're taking delta many of them, so degree of W many. So
Then why didn't we choose the one in the middle as degrees of development?
oh yeah, I just didn't complete the picture, so we can make it have, yeah, so maybe it has another edge like that. Maybe I should make all of these have like degree 2 so that it's better picture. Okay, yeah, so in this picture, W has degree 3, so we're in S, we're gonna take the next 3 vertices, and then in S, everybody has degree 2, which is the next highest degree. Is the picture making sense? Okay, so let's find that sequence of 2 switches. So so this is like proof of the claim, and then we'll return to the main proof. So if the neighborhood of W is not already equal to S, then there's some vertex X in S, which is not contained in the neighborhood of W. So if the neighborhood, say in G of W, is not equal to S, then there is some X in S where X is not in the neighborhood of W. Okay, so let me draw that in the picture. So in this case, this vertex would be X. And then there's also a Z that is in the neighborhood of W, but not inside of S. So, and there is Z in the neighborhood of W, but Z not an element of S. Okay, so in this picture, this is our Z. Do you have a question?
Why do we need the C part of S?
Yeah, so we're gonna need this vertex for our 2 switching. Because I know that that the degree of W is equal to the number of elements in S. Yeah. Yeah, good question. Other questions? Okay, so we've identified these 2 vertices. And then we know that we know the following. So we picked W to be a vertex of maximum degree. So we know the degree of W is greater than or equal to the degree of X, because X is contained in S, so it has lower degree. And W is a neighbor of Z and not X. That means that I think I have this backwards. I think I want this to be I think this is how we want this to be. So we know that X has degree greater than or equal to Z. Right, okay, so what am I looking for? For my two switching, I need there to be, so I'm gonna have these three vertices, but I'm looking also for another vertex so that I can include this edge and then connect Z to something else. So I'm trying to argue that there is going to be some other vertex. And we know that the degree of X is greater than or equal to the degree of Z, because X comes from this set X of vertices with like the next highest degrees, right? So that means that Z has lower degree. And furthermore, we've already identified a neighbor of Z that's not a neighbor of X. So that means that there is a neighbor of X, which is not a neighbor of Z. So there is some element Y, which is adjacent to X, but not to Z. So this, in this case, actually in this case, there's multiple choices for what we could pick for Y. So it could be this vertex or this vertex, but I'll take this one. Okay, does it make sense why the vertex Y has to exist? Okay, so then the two switch that I'm gonna do is I'm gonna delete WZ and XY. So those two blue edges that I have, and then I'm gonna add in WX and ZY. Okay, so I'll draw those in red. So now I have WX and ZY instead of those two edges. Okay, so then what we've done is, what has this accomplished? This has increased the size of the overlap between S and the neighborhood of W. So then to finish the proof of the claim, all we need to do is just repeat this process. It has to terminate because the size of this is at most the degree of W. And then eventually we will have that the neighborhood of W is equal to S. Okay, so that finishes the proof of the claim. So yeah, maybe we'll say continue in this fashion. until NGW is equal to S. And maybe I shouldn't even say, maybe I won't even call this G because it's not really G anymore. We've changed it. I'll just say the neighborhood of W. Okay. Are there questions about the claim? Okay, so now we're gonna assume, so let's go back to the statement of the claim. So now we're gonna assume, we're just gonna work with G star and H star. So we have a sequence of two switches that transforms G into G star and H into H star, where G star and H star both have this property that the neighborhood of the highest degree vertex is equal to the vertices of next highest degree. Okay, so since, so now we're working with G star and H star. So since the neighborhood of W in G star is equal to S, which is also equal to the neighborhood in H star of W, if we delete W, that leaves us with two simple graphs that have equal degree sequences. So our goal is induction here, so that's why we're trying to find smaller graphs. So we're gonna have G prime, which is G star minus W, and H prime, which is H star minus W. Which are simple graphs with equal degree sequences. So by the inductive hypothesis, there are two switches that transform G prime into H prime. And that same sequence will work to transform G star into H star. So in total, to get from G to H, we need to go from G to G star by two switching, and then we have more two switching that gets us into H star, and then we need to undo the sequence of two switches that got us from H to H star. So this is like reversed from the direction that we argued it. So there is a sequence of two switches from G to H. And that finishes the proof. Are there questions? Okay, so now we're gonna switch gears and talk about the next kind of like mini topic for this lecture, which is gonna be directed graphs. So a lot of this is just gonna be definitions and mostly just translating definitions that we already know for graphs into this new setting, which is directed graphs. So a directed graph, oops, make a definition. A directed graph and this is going to be similar to our original definition of graphs. So this is, we'll call it G, is a triple consisting of a vertex set called V of G, an edge set called E of G. And then roughly what we're going to do is assign a direction to each edge. And the way that this is done is by specifying a function assigning each edge to an ordered pair of vertices. And we call the first vertex the tail. And the second vertex is called the head. And usually we say that an edge goes from whatever its tail vertex is to whatever its head vertex is. So just to draw an example, if these are our vertices and these are our edges, how you would usually draw this is by just drawing an arrow on every edge specifying kind of what direction it goes. So let's say this is X and this is Y. Then for this edge, Y is the tail and X is the head. Does that make sense? I think also you might see edges just drawn straight up as arrows, just so you're aware of that. I think maybe the textbook draws it that way, I'm not sure. I usually like to just draw the arrow in the middle because I think it's easier for me to see like what direction every edge is going. Okay, and then we're gonna spend a little bit of time like translating vocabulary that we already know about graphs into vocabulary about digraphs or directed graphs. So this is also called a digraph. So in a simple digraph, so for graphs, we've been used to writing edges just as like YX or something like that. But then in the case of directed graphs, now the direction is important, right? So I would write the edge as YX, but I would not write it as XY, because that means like the edge going in the opposite direction. So when the graph is simple, you can specify edges in this way. In this context, a path is going to mean a digraph where all of the edges are pointing in the same way. So a path or a directed path. So it'll just be a path, but all the edges go in the same direction. And same thing for a directed cycle. Will also mean for will also have that mean that the edges all go in the same direction. Okay, and then some other words. So the underlying graph of a digraph is just the graph that you get from treating the edges as unordered pairs. So you just get this graph by ignoring the direction of each edge. And then to go in the other direction, so if you start with a graph and you want to obtain a digraph from it, then you would refer to the extra data that you need as an orientation. So an orientation of a graph G is a digraph obtained from G by choosing an orientation for each edge or selecting a direction. Yeah, do you have a question?
But in a diagram, that correct. So
No, yeah, every edge has a direction. Yeah. Other questions? Yeah.
Is there a thing that looks like that, like a mixed graph?
So sometimes when people do that, they just draw a digraph where some edges go in both directions. Yeah. So like digraphs come up a lot in applications because a lot of times like you're not just trying to represent things and connections between them, but sometimes you're trying to represent things and ways of going from one to the other. It's like in like an electrical circuit or flight paths or like a lot of different like real life examples. There's like movement involved, right? And so yeah, so usually if you want to say you can go in both directions, you would just draw two edges. So like you'd have like two edges and one goes in each direction like that. Yeah. Are there other questions? And then another like piece of terminology that is used is an oriented graph. So this is just, you can either think of it as an orientation of a simple graph or as a simple digraph, this equivalent. So orientation a simple graph. Or it's a simple digraph. Okay, so one more definition before we get into some results about digraphs is we need a new notion of what it means for graphs to be connected or what it means for digraphs to be connected, because in our old definition, it was like a graph is connected if there's a path from every vertex to every other vertex. But now it's not clear necessarily what that should translate to. And there's kind of two notions of what connectedness is for digraphs. So we'll say that a digraph is weakly connected if its underlying graph is connected. And we'll say that it's strongly connected if every ordered pair of vertices has a directed path from one vertex to the other. Um, okay, so we'll do some examples now because I think that this is like the differences here are a little bit subtle. So let's do just a first example. So the graph with a single directed edge. Is this weakly connected, strongly connected, or both? We have disagreement. So why weakly?
Because you, like, if we call the one on the left U and the one on the right B, we don't have the path from B to U.
Yeah.
Direct.
Do the people who initially said both, does that explanation make sense? Yeah. So, okay, then second question, if we have a directed path of length n, how many strong components does it have? So how many connected components are there when you're thinking of your connected as strongly connected?
Include a cycle.
Sorry?
Can the path include a cycle?
No, so I'm just saying like all of there's one edge between every vertex and they all go like left to right. So every vertex by itself is a component. Because there's like the trivial path from a vertex to itself. Yeah, so there's n, which is the number of vertices. And how many weak components?
One.
Yeah. So same for the ordinary path, we're just gonna forget about the orientations and then we have one connected component. Okay, what about last example, cycles? How many strong components and how many weak components? Yeah. So this is strongly connected and weakly connected. Okay, are there questions about any of this? These examples? Okay, great. So there's kind of an analog of the handshake lemma. So let's talk about that really quick. And there's also a little bit of notation for like degrees now, because at every vertex, there's kind of two different degrees you might think about. There's like the edges coming in and the edges going out. So we'll say the out degree, which is denoted D plus of a vertex, is the number of edges with tail V. I personally find this confusing. I think I agree with out corresponding to tail, but I don't know about plus. To me, this seems weird, but it is what it is. And then the in degree, D minus of V, is the number of edges with head V. Okay, so now we're gonna have a proposition. And this is kind of like a directed version of the handshake lemma. So maybe I'll give you a few minutes to think about what the statement should be. So this is like what is the goal? To relate summing over the vertices of in degree, summing over vertices of out degree, and compare that to the number of edges. So what are we gonna do? All right, what do you guys think? What should the statement say? Does anyone have a guess? Yeah.
Twice the number of the edges is the sum across all vertices of their out degree plus their in degree.
Good, yeah, I think this is true, right? It's like over here, um, you're counting each edge twice, and over here you're counting it by its head and its tail, right? Did anyone come up with a different statement? Yeah,
Total in degree, sort of up degree, number of edges.
yeah, so this is another true statement. Yeah, so with this one, we're counting the number of edges on the left by counting the tails, and then on the right by counting the heads. Good. Anything else? Yeah. So like, yeah, okay, yeah, you're good. Other questions? Okay, so let's talk about tournaments. This is an orientation of the complete graph. Oops. And we'll prove a theorem about tournaments, and that will be where we end for the day. So a tournament is an orientation of a complete graph. So the reason it's called that is that it's supposed to kind of model the following scenario. So if you had a bunch of teams and every team plays every other team, and in every game there's a winner, then for every edge you'd be able to draw an arrow according to which team won. And then the resulting oriented complete graph sort of like tells you something about who is the winner potentially. So like, just to say we have like 5 teams and they each play each other. And then let's say we point the head towards the winner. We might have something like that. Then this is supposed to be, wait, did I get all of them? I'm missing one here. Then this could be modeling like some kind of competition between teams. So let's do an example. I'm going to ask you all a question, which is it possible for a tournament to have more than one vertex with maximum in degree? So like what this is saying is it possible that there's not just one team that has the most number of wins? So I'll give you a few minutes to think about it. What do you guys think? Yeah,
If you flip the direction on the rightmost two vertices on that graph, every vertex is 2 in degree.
so which ones need to be switched?
The one edge between the rightmost two vertices.
That one. And now every edge has, or every vertex has 2 wins and 2 losses.
Mhm.
Yeah, nice. Yeah, so yeah, if we look at this one, every vertex has 2 wins and 2 losses. So we can't necessarily just decide on a winner that way. There's another thing that you might say is reasonable. So like so here's, I'll make a definition. So we'll say a king in a tournament is a vertex from which every vertex is reachable by a path of length at most 2. So I'll draw a picture. So I think I switched the meaning of winning versus being a head. So the textbook wants the tail to be the winner. So I'll just like write that to the side. The tail is the winner. So in this picture, we would interpret this as the win, and this is the loss. Okay, anyway, so a king, so if this is a vertex, and let's say it beats this other vertex. So let's say this is K, and we'll call this one U. Okay, so K beats U, and it's also reachable by a path of length 1. If K loses to V, then what we want is that there's a way to get to V from K in at most 2 steps. Does that make sense? So the like interpretation of the king is that this is someone who either beats everyone, or if they lost to someone, they beat someone who beat that person. Does that make sense? That's kind of the interpretation. Okay, and then we have a proposition. Which is that every tournament has a king. So let's see how the proof goes. So let's let X be a vertex in a tournament. If X is not a king, then there is some vertex Y, which is not reachable from X by a path of length at most 2. So there's a vertex Y such that Y is not reachable from X by a path of length at most 2. So if this is X and this is Y, it's not possible to have X beating W and then W beating Y. This does not happen. So instead, what happens is if W beats X, then that means Y must also beat W, right? So if X beats, or I guess, what should we say? If X for every edge from X to a vertex W, we have also the edge YW. Right, because it's a complete graph and we're orienting every edge. So we have to assign an orientation to this edge. If X beats W, it's not possible for us to go this way, so it has to go that way. And then we also, what else can't we have? We can't have that X beats Y because that's a path of length 1. So it has to be that Y beats X. We also have the edge YX. So that means that the out degree of Y is strictly larger than the out degree of X. Okay, so let's again recap why that's true. For every edge contributing to the out degree of X, we have a corresponding edge contributing to the out degree of Y, and furthermore, Y has one additional out degree going to X. Does that make sense? So then if Y is not a king, then we'll repeat this. To find yet another vertex, Z, that has larger out degree. And this has to terminate because the graph is finite, and at which point we've found the king. And that finishes the proof. Are there questions? So the thing that we've also proved with this proof is that every vertex of maximum out degree in a tournament is a king. So it's easy to identify the king. And I guess a corollary of that and the example from before is that the king is not unique in the tournament either. So that's not really a criteria for like determining a specific winner either. Okay, so that finishes chapter 1. So next week we'll pick up with chapter 2, which is all about trees. And you have a problem set due tomorrow, so remember to do that. And I hope you have a nice weekend.